Hello. Today we're going to talk about the amplitude and phase of the steady state solution. But first, let's review some ideas from before about undamped forcing and resonance. Recall that we like to consider the forced harmonic oscillator. That is y double prime plus p times y prime plus q times y equals g of t, where g of t corresponds to sinusoidal forcing. That is, it's the function k times cosine omega t minus theta. We will assume that p squared is less than 4q so that the characteristic polynomial has complex roots. That is, lambda is alpha plus or minus beta I. Whenever we have a certain condition on the frequency omega, the general solution is in the form y of t is equal to k1 times y sub 1 of t plus k2 times y sub 2 of t plus y sub p of t, where y sub 1 is e to the alpha t cosine beta t, y sub 2 is e to the alpha t sine beta t, and y sub p, our particular solution, is capital A times cosine omega t minus phi. Notice that there is a dependence on the amplitude capital K, the angular frequency omega, and the phase angle theta. Recall that our particular solution has amplitude capital A, which is k divided by the square root of q minus omega squared plus p omega squared, and the phase angle phi, which is theta plus curly theta, where cosine of curly theta and sine of curly theta can be expressed in terms of q minus omega squared and p times omega. We are interested in the following motivating question. What happens when the frequency omega satisfies q minus omega squared plus p omega squared equals 0? Our goal is to consider the solution y of t as we vary the frequency omega. We notice that we can always find various conditions for the amplitude capital A. That is, if our frequency omega is less than the natural frequency beta, then the amplitude capital A is approximately capital K divided by beta squared minus omega squared. On the other hand, if the frequency omega equals the natural frequency beta, then capital A is approximately capital K divided by P times omega. And if our frequency omega is greater than beta, then capital A is capital K divided by omega squared minus beta squared. In other words, the amplitude capital A is very large when there is little damping, that is, alpha is approximately 0, and the frequency omega is close to the natural frequency beta. This phenomenon is known as resonance. On the other hand, the amplitude A is very small when the frequency omega gets very large. The phase angles phi approximately equals to theta when omega is less than beta. The phase angle phi is approximately theta plus 90 degrees. That is, phi and theta are 90 degrees out of sync when the frequency omega is near our natural frequency, beta. And finally, the phase angles phi is approximately equal to theta plus 180 degrees. That is, they are 180 degrees out of sync when the frequency omega is large. We found that there is a graph that gives us an approximate value of our amplitude capital A. Again, if the frequency omega is very near the natural frequency beta, then we have the concept of resonance. This is the peak that we see in the graph, where here we plot A versus the frequency omega. Now, if we go back to the non-homogeneous second order equation, we'll consider the special case when we really do have resonance. That is, P is equal to 0, Q is equal to beta squared, and omega, our angular frequency, equals beta. We found that we cannot make a guess of the form y is equal to capital A times cosine omega t minus phi, because it turns out that this now will be a solution for the homogeneous equation. Instead, we find that there is a particular solution of the form y sub p equals capital A times t times sine of beta t minus theta, where capital A is capital K over twice beta. And so we can express the general solution as a combination of this function y sub p, as well as cosine beta t and sine of beta t. Today we'd like to focus on the amplitude and the phase of our steady state in a bit more detail. Let's return back to our non-homogeneous second-order equation. Recall that we have a forced harmonic oscillator, and we will focus on the case where we have sinusoidal forcing. That is, our forcing function g of t has amplitude capital K, angular frequency omega, and phase angle theta. As before, we will assume that the damping is not too large, that is, p squared is less than 4 times q. In this case, the characteristic polynomial has complex roots lambda equal alpha plus or minus beta I. The extended linearity principle asserts that the general solution to our non-homogeneous equation is y of t equals k1 times e to the alpha t cosine beta t plus k2 times e to the alpha t sine beta t plus y sub p of t. This function y sub p of t is called a particular solution, and we found up to this point in the course that we have two possibilities. In the first case, let's say that q minus omega squared plus p omega squared does not equal to 0. Then there is a periodic solution of the form y sub p equals capital A times cosine omega t minus phi, where capital A we can express as capital K divided by the square root of q minus omega squared plus p omega squared, and capital V, our phase, equals theta plus the arctangent of p omega divided by q minus omega squared. In the second case, let's assume that q minus omega squared plus p omega squared equals 0. In this case, there is a solution of the form y sub p equals capital A times t times sine of beta t minus theta, where capital A, our amplitude, is capital K divided by twice beta, and phi, our phase angle, equals theta plus pi over 2. Recall that as long as p is positive, all solutions y of t are approximately equal to these particular solutions as time increases without bound. There's a very nice YouTube video that gives a practical application of all of this. It shows a video of a mass attached to a spring, and this entire system is being forced sinusoidally. You may want to look at this video to get a better idea of what we're going to talk about next. The idea is that here we have a system where we have a forced oscillation, and there really are three possibilities as we increase the frequency omega. Either omega is less than a resonant frequency, omega is equal to a resonant frequency, or omega is greater than a resonant frequency. However, how do we really know that we have a resonant frequency when the amplitude doesn't increase linearly as a function of time? Well, we'll try to explain that concept next. Let's assume for now that our damping P is not too large. That is, P squared is less than 4Q. However, we just can't assume that there is no damping, that is, P is equal to 0, because this is unrealistic. So we may as well assume that there's a little bit of damping, that is, P is greater than 0. Recall that if our forcing term, g of t, is sinusoidal, that is, it's capital K times cosine omega t minus theta, then the response, y of t, is always approximately another periodic function, capital A times cosine omega t minus phi. Here, our amplitude, capital A, and our phase angle, phi, are both functions of the frequency omega. You can see here on your screen a plot of this amplitude, capital A. You'll notice how it appears that somewhere in between the middle of the graph, we have a peak for our amplitude if we view this as a function of omega. Of course, the size of this peak depends upon the damping. Whether P is very large, we see that the peak is not very great, whereas if P is smaller, then we see that the peak seems to increase. Our motivating question for today is, what is the largest amplitude that we can find, and at what frequency omega does this occur? Again, we're going to assume that there is at least some damping, but we'd like to know what can we say about the size of this peak. Let's assume that the roots of our characteristic are complex numbers, which we'll express in terms of alpha and beta. We'll also assume that we have sinusoidal forcing. First, the maximum amplitude that we can get depends upon our choices of alpha and beta. If alpha is less than or equal to beta, the maximum amplitude is capital K divided by the absolute value of twice alpha beta. On the other hand, if alpha is greater than beta, then our maximum amplitude is capital K divided by alpha squared plus beta squared. Next, notice that this maximum occurs at one of two possibilities for the frequency. Either the frequency omega is the square root of beta squared minus alpha squared, or the frequency omega is equal to 0. In particular, there is a non-trivial, quote, resonant frequency, unquote, only if alpha is less than beta. We're putting this in quotes because we don't necessarily have alpha is equal to 0. That is, that we may have some type of damping. Typically, we only use the word resonance if alpha is equal to 0. There is no damping. But we can see that we do have a peak in the amplitude A for some value omega as long as alpha is less than beta. And finally, we can say something about the phase angle. At the maximum value of our amplitude A, we have phase angle phi equals theta plus either the arctangent of omega divided by alpha. This is when omega is equal to the square root of beta squared minus alpha squared. Or phi is equal to theta. This is when we don't really have a, quote, non-trivial resonant frequency, unquote. That is when alpha is greater than beta. Now let's explain why all of this is true. Recall that the amplitude, capital A, is a function of the frequency omega. And in fact, the maximum value of this function occurs when the derivative vanishes. So let's find a formula for the derivative. Since we're assuming we have complex roots, let's express P and Q in terms of alpha and beta. Then dA d omega can be expressed in terms of alpha, beta, and our frequency omega. In particular, if we set this equal to 0, then we find either omega is equal to 0 or omega is equal to the square root of beta squared minus alpha squared. Notice that the latter, that is omega is the square root of beta squared minus alpha squared, can only occur if alpha is less than or equal to beta. If alpha is greater than beta, then we're taking the square root of a negative quantity, and in that case, the frequency omega doesn't make any physical sense. Once we've determined these two values at which the derivative vanishes, we can then plug these in to find the maximum values both for our amplitude and for our phase angle. For the amplitude capital A, we have one of two possibilities. If omega equals 0, then our amplitude is equal to capital A, k, divided by alpha squared plus beta squared. On the other hand, if omega equals the square root of beta squared minus alpha squared, then our capital A equals capital K divided by the absolute value of twice alpha beta. We find similar formulas for phi. If omega equals 0, then phi just equals theta. On the other hand, if omega equals the square root of beta squared minus alpha squared, then phi equals theta plus the arctangent of omega divided by alpha. This explains how when we do have the case when alpha is less than beta, we can find a certain frequency omega, namely the square root of beta squared minus alpha squared, such that our amplitude capital A will reach a peak, and we can say what happens to the phase angle phi. Thanks for watching.